Hello, this is Arbabayev here. This is my final project for the Cyber Physical Systems course, and first I'll do a little bit of a demonstration of it to show how it works, and then I'll talk about it and I'll do some other things on it, and just to demonstrate this project. First, let me show what it does, right? So if I do this, you can see it tries to keep the top platform level. Now, um, depending on the depending on the gains that I have on this dashboard, it responds differently. So if I set the gains aggressively, like for example, if I add like my proportional gain high, it will respond fast, but it also creates the oscillations, which you showed before. So what is this? So this is this kind of technology can be used, for example, on a boat to keep the desk level, regardless of the waves rocking and rolling the boat, and this kind of technology can be used to filter out all those disturbances and create a level desk. Or it doesn't have to be a desk; it can also be like a satellite dish platform. Of course, you would need to add a third yaw axis for that. Right now, it has two axes, pitch and roll, but for that kind of application, you also need a yaw axis and probably have one more sensor there as well. It can be used for stretcher, uh, so that when you have a patient on the stretcher and they are on this vehicle, and let's say it's moving fast on a bumpy road, you want to make sure that the patient is kept relatively undisturbed. So this kind of technology can be applied to that as well, and or it can be used as a gimbal for cameras on attached to a drone or another vehicle, so you can set the angle of it, and then this kind of technology can keep it um, to that angle. Now here I also have a joystick which I can use to set a certain angle for it, and then it will try to keep that angle. It doesn't have to be like horizontal, so I can set an angle for this. So let's say I put it this way, and then if I move, now it will try to keep it on that angle. If I change it, and it should try to keep it. Now right now my gains are not ideal. I just put them a little on the high end just to show the responsiveness of it a little bit better. Um, so so for example, I can actually turn off those gains completely, put them zero, right? And what that will do is it will effectively basically turn off the motors, servos, and that would allow me to, for example, to fine tune the complementary filter coefficient. So if I can take it now, it's not gonna move, like it's not gonna do anything, right? As you can see, because I turned off the motors. On the graph, you can see that you can now see the full range of the motion without this trying to minimize it. And right now it is set at tau 0531, 0525. I think is about the optimum value for this tau coefficient of the filter, complementary filter. So if I put that, like for example, to zero, so I'm basically turning off the filter now. As you can see, all these disturbance, like all this error, is just passing through, and that's why you have this unfiltered, basically, that data coming through. And if you put the tau now to very high, now you'll basically overfilter it, basically, right? Now you have a much smoother curve, but that also is not ideal because now you can get lag there. So if it's too smooth, then you'll have some lag. So I'll put it to predefined optimum value of it is about 0.52 ish, and then I can set the my gains at relatively optimum values, and then now if I do this, now it's more stable, it doesn't vibrate as much, but it's a little bit sluggish because of that. So there's a bit of trade-off there, right? It still does what it is supposed to do, you see. And then I can again, as I said, I can set the angle, and as you can see, as I move it, it tries to keep its heading to that angle, and I can just put it there and play with the joystick as well, and turn it as I want. And of course, I set some hard limits for the joystick so that it doesn't, accidentally rotate too much and damage itself. Okay, so how does this satisfy the assignment requirements? So let me talk a little bit about that. So the assignment requirements, so the first requirement was the wireless communication. So I have a wireless communication going on here between my Pico 2W microcontroller and the computer through Wi-Fi using UDP protocol, and choose UDP so that if there's any delay in this communication, or then that basically won't affect the logic of Pico, and it will always get the latest results, and if it misses it, it just drops and moves on. So that's why I used UDP. And for the wired communication, I'm using I2C to communicate, for the communication between IMU. So I have the IMU sensor here. It's sending its data, which is accelerometer and gyro data, over those wires using I2C protocol to Pico. I'm also using I2C protocol on a different channel to communicate some of this telemetry data, to send that telemetry data to the LCD screen here. And this data is basically the same kind of data as I have here, which shows the target and actual. So now, if this was far away from this one, right, then this would allow both local visualization of that telemetry and as well as remote visualization of it. So that's basically the idea here. Okay, so that's wired communication, and then of course this joystick is analog actuator. So basically it sends the analog signal, analog voltage, to Pico, and it's connected to the ADC, analog to digital converter enabled pins of the microcontroller, and that's how I'm implementing that requirement there. So basically this is like a potentiometer, two potentiometers there, right, for X and Y axis, and that's how it's using it. And then for Pico to send the signal to the servo motor, so I have two servo motors there, and those servos receive pulse width modulation data, and then they are attached to those pins that are that can handle that, and that's basically a form of digital to analog conversion. And then for the state estimation, as I mentioned, I'm using complementary filter to filter out the noise from the accelerometer and also filter out the drift of the gyro, and then fuse them together to get more accurate representation of the measured angle. And that complementary filter is being implemented there to fuse those together to filter those out, and tau of that coefficient of it can be set using the dashboard. Yes, and then for feedback control, I'm using incremental PID, and the reason why I'm using incremental, not the regular one, is because the error of this platform is not only a function of the position of the IMU sensor, but it's also this function of the angle of the base of those motors. And angle of those motors is not, as you can see here, for example, right, in this position, this angle here of this motor is not being measured. And as it's not being measured, and if some servos would have another wire that can be used to that basically sends back a signal to tell the actual position of the servo. If I had that, then I could use it to calculate the actual error, and basically that would allow us to use the standard PID control. But unfortunately, those cheap servers that I have here, they don't have that capability. So because of it, I have to use incremental PID, which is basically a derivative of the standard PID, and just to calculate this adjustment step, and then just keep adding that to the previous one, which basically is like integration. So you take the derivative of it first and then reintegrate it, basically get the same thing, more or less. And yeah, so and I tried different things with that. One thing I noticed is that this derivative term here, KD, it just basically is useless. It's just, if you set it anything but 0, what it will do, it will just amplify the error. And it's because you're taking the derivative of the error, and when you have a high frequency error, its derivative will be even, you'll get very, because of those high frequency signal, we have very steep angle, right, rate of change, and that basically is its derivative. So you will get very high derivative numbers there, and that creates a that just amplifies the error. So if I, for example, if I just increase this KD for the roll, I'm just giving it a little bit, and you can see if I touch it a little, so you can see how it is making it, how it is affecting it, right? So you don't want that, that's why I'm setting it to 0. All right, so yeah, so again, just to play around with it, it's a bit of a fun, really, to play around with this thing. And yeah, so that's that. Thank you very much. Yeah, thank you very much.